Now,
spengere le luci, scusa.
we can switch off the light, or well, there is enough light from the outside.
I don't quite know why this slide is but reduce this a bit. There's a chord. How about that?
So, as I announced this physics talk, what does it mean? That, I mean, the mathematics, physics uses mathematics, but this physicists, theoretical physicists use it mainly formally, manipulating formulas, very often in an exact way, but when I will say we can show and so on, this will be at the level of physicists mathematics. I will mention also some rigorous results, but here I want to speak mainly about main ideas and the role that large fluctuations have played in the last, let's say, 15 years or 20 years. Okay. So the abstract you have already seen is just what. I have many slides. I will use only part of them. Because, now, the first question. I mean, thermodynamics has been a very successful theory and was founded almost 400 years ago, and statistical mechanics provides a model for thermodynamics, and you do the rigorous deductions essentially in statistical mechanics. But while at equilibrium we don't have to solve equations of motion, because more or less the Gibbs distribution is given for free. You just have to know the Hamiltonian, and the situation is entirely different out of equilibrium, because you have dynamics must enter one way or the other. That is the main. So I will speak only about as we shall see in a moment. The richness of non-equilibrium phenomena is enormous. So the difference with respect to equilibrium is, or thermodynamics, we cannot hope for a general theory which is good for every phenomenon, but we have to select. And I think that some progress in the last decade or maybe 20 years has come from trying to understand diffusion phenomena. And diffusion is almost ubiquitous phenomenon, and you see, there are important mathematical models which have been studied rigorously, which have played more or less a role similar to what the Isaac model played in the, for example, in the theory of critical phenomena. In the theory of critical phenomena, renormalization group methods have been very effective, but in most of the cases they are just heuristics, not rigorous deductions, except for a few situations. So here, I think the first thing I will try to convey is why large deviations have played such an important role. The fact that in physics light deviations were not, certainly were not known under this name in the past, but the first example of a large deviation estimate and definition of thermodynamic functions in terms of large deviations is due to Einstein, as many things go back to him. In a paper which is not among his popular, but I will give you the reference, because the second part of the paper is completely wrong, but the first part is very beautiful, and he was mistreated by his contemporaries. There is a very rough statement in a paper by Jost and Zernike, who understood what was happening at the fact that at the critical point there are long-range correlations, and they said Einstein, if he continues like that, he gets nowhere. And no, his mistake was that he, at the critical point he had considered stochastic variable as an independent variable. And that was due to the long-range correlation, that was not correct. Okay. Oh, just to tell you the spread of non-equilibrium phenomena, I will list just a few of them, which are, in these days we talk a lot about hurricanes. That is a typical non-equilibrium phenomenon. Then you have a galaxy. Also, this is a non-equilibrium system. Then, I mean, in biology, there is you find all sorts of non-equilibrium phenomena on many scales of time. And for example, molecular motors, which were discovered some 30, 35 years ago, you see, these are motors which transform chemical energy into mechanical energy, mechanical movement, and you see, they're really, I mean, this is not, it's a kind of caricature, but it's really, the real molecular motor is done something like this. And you see, when I move my arm, there are milliards of molecular motors which do the work. And so, for example, also the splitting of the double helix in DNA is done by molecular motors. So they do all sorts of work that is needed at the molecular level. Also tectonics, this is the famous, in California, there is, I don't know what is the English name.
Or a chasm.
Okay. And of course, this is also a non-equilibrium phenomenon. So, these are the concepts of equilibrium and non-equilibrium belong both to mechanics and thermodynamics. Here I will be more interested in the thermodynamic point of view. And of course, the ideal would be to have very simple principles, like we have the one in thermodynamics that I will recall in a moment. And there is one important point to understand, that classical thermodynamics is used to understand transformations from one state of equilibrium to another one. And so people invented the idea of quasi-static transformation, which is a succession of equilibrium states. So it's a transformation which lasts in principle an infinite time. But the point is that this is not a consistent concept, because I mean, to move a state even on an infinitesimal time, you need to go out of equilibrium. So this was made clear there is a famous treatise on thermodynamics by Callan, and there is also a picture in Callan's book. Suppose that this is the surface of equilibrium states, but then the transformation is a discrete sequence of equilibrium and non-equilibrium states. So they will appear on this surface as a discrete sequence. And that is what it makes clear in words, but I think that was a very important observation. Okay, the principle of thermodynamics are very simple. You have conservation of energy, so in the transformation, the sum of mechanical and heat. So heat is a form of energy, and it is. And then we are interested more in the second principle. Second principle, there are many formulations. But the one which is of interest to us is the fact that you can define a function of state, which is called entropy, and which has the property of being maximal in an equilibrium state. Now, what is entropy? Entropy, from a thermodynamic point of view, is not so easy to understand. You see, if you read I've tried to read the Clausius papers. Clausius papers are very beautiful, I mean, and maybe a little bit long for our present taste. But, and in fact, I mean, the first question you ask, how did he think of it? But then reading more deeply, especially in his fourth memory, then you understand that he wanted to characterize all equivalence. The entropy is a function of state. So you have initial and final state, but I mean, all reversible transformations are equivalent to go from one state to the other. And he wanted the quantity to characterize numerically all the equivalent reversible transformation. So that was, and that is, in fact, can be understood. So you have then the statistical interpretation is due to Boltzmann. Actually, people say, okay, this is the famous Boltzmann relationship. This W is the number of microscopic states compatible with the macroscopic parameters, so it's essentially proportional to the probability of a state. He introduced probabilistic reasoning. Now, this equation is on the grave of Boltzmann, but actually it was never written like this by Boltzmann. It was written by Planck. And both, as we shall, no, I will not talk about Planck, but Planck was quite hard on Boltzmann because he criticized this constant. Actually, Planck said how much it has to be, and that was the beginning of quantum theory. But we shall see that also Einstein was not so. Okay, then there is of course the Shannon entropy, which in statistical mechanics is called also Gibbs entropy. And apparently the name, this is just a story, that von Neumann said to Shannon, you have to call it entropy because actually nobody knows what entropy is, but then you will be always in an advantage position. Anyway, okay. Now, what are the states which are closer to equilibrium, at least conceptually? States which also do not depend on time, and stationary states. States, for example, if you have a conductor in which you have a potential difference, then there will be a current flowing. And if the potential difference stays constant, the current will be constant. This is a stationary state. The same for a bar, an iron bar between two temperatures. Then there will be, so typically stationary states are characterized by the fact that you have a system and there is something flowing through it. So there is a current. Current is a thermodynamic variable, but it's more complicated than the usual ones because in its definition it involves time. As we shall see, we shall have to do some space-time thermodynamics. Okay, now progress has been made by studying fluctuations in these stationary states. Now, at this point that we go back to Einstein, so, I mean, this is typical setting of an non-equilibrium situation. You have some reservoirs, you have your system, and these reservoirs are connected with the system, and there are currents flowing through the system, which can be also simultaneous, like heat and electricity, for example. In fact, there are many famous relationships discovered in the 19th century between this type of conductions. So, as I said in the abstract, the most important question is whether it is possible to formulate some general principle, and the first thing you have to do is to define the analog of what are thermodynamic functions like free energy, entropy, which are connected. I mean. And that is where large deviations come to help. Because in a system in which a current is flowing, you don't know really how to define microscopically. People speak usually of production of entropy. That can be defined in the sense that there is always production of heat, and the reservoirs are usually big systems considered in equilibrium. So, okay, so let me speak now about Einstein. So you see, if you are very near to equilibrium, this problem does not arise. Because, for example, you can expand the entropy. I mean, the entropy is at the maximum, so you have, you can make an expansion to second order, the first order term is missing. And then you always reduce yourself to calculations in equilibrium. And that is the basis, for example, of Onsager theory, which was formulated in the 30s and then taken up again in the 50s. And I mean, which has been really a source of understanding and applications for 80 years, but is used very often beyond its validity. But since I don't, at that time we didn't have anything better. This was a typical pragmatic way of behaving of physicists. Okay, now we go to this Einstein paper. And I quote Einstein. What he wanted, the paper is devoted to a problem. You see that you want to understand what happens in, for example, in boiling water. At some point you don't see anymore through the water, so it's not anymore transparent. And that his idea was that this was due to fluctuations. And but you see, he says that this relationship, as it is not very useful, because in order to calculate the microscopic states which are compatible with the macroscopic situation, you need a theory. And the theory of the microscopic situation, which may be different for every system. So, and it's very complicated. It's very easy to calculate this quantity W for an ideal gas. But as soon as there is interaction, the situation becomes much more complicated. Okay. So you see, his conclusion was, considered from a phenomenological point of view, this equation appears devoid of content. So it's quite definite in his opinion. And okay, then he explains that he can give some meaning to these probabilities in terms of ergodic theory, but this I don't want to discuss. Now, suppose now you invert the previous equation, and then you solve with respect to this, it's called usually thermodynamic probability, but you can normalize it, and then you can express this probability in terms of the entropy. Now, the point is that on the entropy, you can somehow put your hands on from thermodynamics. And so his idea was that one should read this equation in the opposite sense and use it to estimate probabilities. And you see immediately that this has the character of a log deviation formula. And then you can somehow determine the constant by introducing the maximum of probability, so for which this normalized probability is 1. So, see, if this is the state of maximum probability, this quantity is negative, and in front there is a very large number, which is the ratio of Avogadro. This is what is called the Boltzmann constant, which is the ratio of the Avogadro's number over the gas constant. And so he writes this, this is the, you see, I'm still quoting Einstein. So this is his formula for equilibrium fluctuations. And you see, the role played by this difference, S minus S naught, is just the rate that appears in the fluctuation formulas. So you see that you can invert the situation and say and define entropy in terms of log deviations. So log deviations in this case, the log deviation functional is a genuine thermodynamic functional, and this is the entropy in this situation. Okay, then there is another unpublished manuscript, which is not, for strange reason has not been included in Einstein papers, which have been published in Princeton. But anyway, Duplantier translated it into French, and it's a very interesting because it's a talk that he gave at the Zurich Physical Society in the same year, so it was again 1910. Here he declares explicitly what is his ideology: to use this relationship to compute probabilities, and not the other way around. And then he applies this formula, and it has two very interesting deductions. One is the fact that, you know, suppose that you have a small ball which falls in a fluid. Then this acquires a constant velocity, which is given macroscopically by Stokes' law. And you see, mu zero, mu is the mass of your sphere, for example, and mu zero is the liquid displaced. So, Archimedes, okay. And this formula has been verified. Now, from this formula, he obtains the law of Brownian motion, so of the Wiener process. Why? Because he combines this formula with Stokes' law, which tells you that after a time tau, the rule to calculate the displacement is this one. So you have this if a sphere falls down, you have this displacement, and then you have the contribution due to the fluctuations. And he assumes that fluctuations are independent everywhere in different. And then in a very simple argument, he finds that the square of the displacement is proportional to time. He was very, very capable in connecting things that apparently were somehow far away. This is typical of his way of reasoning, because with the special relativity he did the same thing, because he said, okay, we don't understand, we don't see any effect of relative motion, so let's take this as a principle. And so he had this capability of simplifying enormously the situations. Okay, so we learn, so what have we learned? We have learned that, in fact, you can read this formula, Boltzmann formula, written by Einstein, as a large deviation formula, and define the entropy as the large deviation functional. I mean, this somehow has not been used widely by physicists, but if you take the Bible, which is the books by Landau Lifshitz, and you take the book on statistical mechanics, there is a chapter devoted to them. And you see, once we are out of equilibrium, since we don't know how to define directly the thermodynamic function, but let's try to understand what it means this in Boltzmann formula read a la Einstein. You see, you have this quantity, S minus S0. Now, if the system is isolated, this is related in a simple way to Helmholtz free energy divided by the temperature. Now, this difference of F minus F naught is not is something that you can measure in principle. Is the minimum work that you have to do to bring your system in a reversible way from the equilibrium state to the fluctuation. So it's now the concept of minimal work retains its meaning also out of equilibrium. So that is so if you take the logarithm of the probability of for fluctuations in a stationary state, this can be interpreted as the minimal work. And this is what happens in, for example, in lattice gases. Also, you can show that this is the correct interpretation. Okay. So, but the complication that you have in a stationary state is the fact that you have a current. So let's concentrate on a special class of phenomena, which however is a very wide class, which are diffusion phenomena. Because even when you connect your system to two reservoirs, for example, two different temperatures, in the end the system will go to a stationary before going to equilibrium together with the reservoirs, there will be a long stretch of time where the process can be defined by diffusion. There will be diffusion of heat along, for example, a bar. Now, the typical equation for diffusion processes are, since you have conserved quantities, like the mass is conserved inside the system, or we don't include momentum and energy, but because you neglect inertial effects in the diffusion process. And so the equations have this form, so they are conservation equations. This rho may be a vector which describes several thermodynamic quantities. Okay. Now, a concept which is important in classical thermodynamics is that of constitutive equations. So suppose usually everything is based on the concept of local equilibrium. So the idea is that there are different scales in the phenomena. You see, I will give you a series of ideas which actually are physical principles, not they're not yet only partially deducted from models, which so what happens locally, because you may have a situation very far from equilibrium. For example, you may have difference in temperature or electric potential which are very large. But locally, the system may be in equilibrium in the sense that at macroscopic distances, but much smaller than the size of the global system, the system goes locally to equilibrium, much faster, in a much faster way than the whole system. So this is in words, this can be formulated in a clean way for lattice gases or system of this kind. And so you have a separation of scales. There is let's say, a small time scale in which the system locally goes to equilibrium, and then there will be a hydrodynamic scale, macroscopic scale over which the system moves as a whole. And so you see, these two terms are quite clear what they mean. So yeah, this is the diffusion coefficient, which in general will be a nonlinear function, and of the thermodynamic variables, and you have gradients. if you have gradients, then these are cause a current. And this is what is called the mobility or conductivity. If you have an external field which is not too large, in fact, in lattice gases typically is of the order of 1/n, so the number of sides of the system. And these are quantities which can be measured. I thought it was easy to measure these things, but this is not the case. To measure with some precision the diffusion coefficient. But people are doing this now, especially in biophysics. They need this. You have molecules in a solvent, and people have done measurements of the diffusion coefficients or the mobility for very different values, for example, of the density. Okay. Now, and this is true, I mean, and Milton talked about that. I mean, we can, for lattice gases, for models, microscopic models on a lattice, there are many cases where we can prove rigorously either hydrodynamic equations, which have exactly the form that I have indicated. So just this form here. And actually, for example, the diffusion coefficient is given by variational principles and so on. So there are parts of these models which can be controlled mathematically. Now, to study fluctuations, we have to do something else. And this is again something which goes back to Landau. The idea is that you add to the idea is that the fluctuations are due, I mean, you consider usually very often are thermal fluctuations, but maybe also of a different kind. And in thermodynamics, you control only a few degrees of freedom, but your system is microscopically is subject to something that you describe as fluctuations. And so it's, the assumption is that your system is subject like something like an external field. An external field that is fluctuating, or an external force which is fluctuating. Then you see, this explains the appearance in the correlation function of the white noise of this conductivity matrix, and K is the Boltzmann constant, which has to appear there. And the Boltzmann constant is a very small number. So we are in a situation of weak white noise. Now you can put back this expression. So the current will be the hydrodynamic current plus some disturbance. If you put this back in the hydrodynamic equation, you get this equation, and as I emphasized in my seminar 2 weeks ago, this equation is very singular, more singular than the present theory allows. But maybe we may avoid a theory of this equation. Why? You see, takes this relationship and bring this typical current on the other side. Now, this is a Gaussian process. So Gaussian process we know how to treat and what is the distribution, and also to calculate large fluctuations. And for example, for this white white noise in time and space, well, there is also a theory done with this higher regularity structure that Weber and Heidel have done with
Gandhi, is the Einstein relation, which expresses the relationship between the diffusion constant and the temperature and the mobility, etc., is that a phenomenological thing, or is it something derived
no,
from physics?
it comes, he obtained that from his theory of Brownian motion. But then locally it's assumed to hold. What is the Einstein relationship? The diffusion coefficient is actually related to the mobility by the second derivative of the equilibrium free energy. So you see, this is an interesting relationship because it tells you that actually you could define the free energy in terms of dynamical quantities, like the diffusion coefficient and the mobility. So you can have, once you take a wider point of view, also classical thermodynamics falls within it. Okay. Of course, you have two constants of integration. But this is the derivative with respect to all the thermodynamic value. Okay. You see, from this relationship, this here, bringing this on the other side, you can guess the following formula for black deviations. And this is, the whole theory that I will describe follows only from this formula. So it's not actually necessary for what I want to describe to have a theory of this equation. So maybe it can be avoided, but anyway, however, all the results we get from are the same that you would get by assuming that this equation is perfectly meaningful mathematically. So there is something to understand here. Okay, now this formula is very simple because it's quadratic in the fluctuation. There is what kind of, you see, this is, you consider fluctuations which depend on space and time. And what kind of role you think always of the density you have to put in. You have to put, given the fluctuation, you have to put the solution of this continuity equation. But as I said in my previous seminar, the interpretation of this formula is quite simple. I mean, we physicists and engineers learn in school, in our system once also mathematicians have to study physics, not now. But you see, the inverse of the conductivity is the resistance. So you see that this is the power dissipated in a certain interval of time by this extra current produced by the calculation. So the physical interpretation is quite clear and very simple. Okay, of course, I mean, this formula is for the case of equilibrium. So, So you have to guess what this formula becomes when you are out of equilibrium, but only in a stationary state. Okay? And your fluctuation may depend also on space and time, on both of them. Okay? Because this is very important, because we shall see later that this formula actually includes cases. Well, I will speak in after about the additivity principle that was proposed by Bodino and Derrida years ago. And this is one way of looking at this formula is a generalization, which however implies existence of phase transitions. Okay, so what is the generalization? So you are interested in a fluctuation. Now, so you suppose you have a stationary state. So you have a state which is constant in time. So if this is time. Then a fluctuation, what does it mean? First of all, the system must go out of this stationary state. So there will be an initial condition. Okay. And then it will follow a certain trajectory. So if you want to calculate the minimum work to have this fluctuation, there will be a term which describes which is the lag fluctuation for the stationary measure. And this will give you the probability of the initial condition. Then there will be a trajectory, and that will be given, you see, I mean, our formula includes time dependence, so includes the trajectory. You see, the term associated to the stationary measure is it will correspond to this S0 minus S in Einstein formula, because that was foreign to. By the way, am I speaking too much as a physicist?
No.
No. Because you see, a colleague of mine, a mathematician in Rome, once he told me, all your formulas have no meaning because you don't specify when are they hold and so on and so forth. So for me, they are just metaphors. And I say, oh, okay, they are very good metaphors because all our technological civilization is based on these metaphors. So that is a quite casual or cavalier use of mathematics. But okay, so this is the structure, and so there will be in this minimal work, you will have a term that I call the quasi-potential, or which will be the analog of this S minus S0 in Einstein's formula, because this will be the lab deviation functional for the stationary measure. And then there will be this term here, which is just our friend here, this integral. Okay. So. Okay,
So
and
the T0, T1 are the times, not the temperatures in this formula.
no, there is no temperature because maybe you are considering the case in which you have two thermostats.
Yes.
So the temperature changes along the
I
system.
see, but I thought this might be the minimal work to get you from T0 to T1. That's not what you mean.
No, T is time now.
Right.
T is time, sorry. Because I don't use any more temperature. So from now on, capital T is time. No, you are right. That was confusing. Since the system is assumed, the dynamics is assumed to be Markovian at the macroscopic level, so in the sense of current, in the sense that you can express the current in terms of thermodynamic variables at the same time. Okay, so then in the book of Lau-Lifshitz you find essentially well, they call this the minimal work, but they consider only the equilibrium case. So there is essentially only the first term. They don't consider the situation of trajectories. Okay, so what do you substitute for the Boltzmann constant? You see, the Boltzmann constant contains the Avogadro's number, so essentially it's the number of degrees of freedom that you have in your system. So here you assume that each molecule occupies a certain space, which is of the order of the mean free path in the collisions, and so this is a scaling factor, which is of the order, you see, is essentially a ratio between a typical microscopic length scale and so typical intermolecular distance, and then the macroscopic unit. And so you see, what interests to us is that this is a very large number. So this qualifies the regime of. And then the rate function, which contains this, which will be the analog of the free energy in Einstein's formula. And then you have this dynamical part, which will be associated to the trajectory. Now, and then I will show that in fact the two things are related. The life deviation functional for the invariant measure and is connected with the variational principle for this dynamical part. Because essentially it will be connected with the trajectory that leaves the stationary state and reaches the fluctuation. Then we shall determine what is this trajectory. Okay, but this we shall see in a moment. Okay, so you see, this formula from which we started contains both thermodynamic variables and currents, and they are related in some way. Now, so it describes a kind of joint probability. So we want to eliminate the currents and find something only for the thermodynamic variables. Okay? So, you see, these are the two things are related by continuity equation. Now, in the continuity equation, you can add to the current any current which is divergence free, because it is zero to the divergence of the current. So you take. I think probabilists are familiar with when you want to prove life deviation for independent variables to the Kernel procedure. You change your distribution in such a way that the fluctuation becomes typical. And this is exactly what you do. You introduce another field in such a way that your fluctuation becomes typical. Okay? I think this procedure was actually, in spite of the fact that it is a paper very difficult to read in a paper by Kipnis, Sol and Varadan, which is, at the time when it appeared, some 30 years ago, was unreadable. But hidden, there is this same idea of grammar. And so, okay, then you introduce this, and then you minimize over all the currents which satisfy this continuity. And this can be solved exactly. This can be done in this way. You write your external field as two pieces, one which is a gradient of something and one part which is non-gradient. Then you insert this into the formula, and in the end, I mean, it's a rather, it's not a trivial computation. But at the end, you discover that your functional can be expressed as two essentially independent terms, two quadratic terms. So it's as if the two things were orthogonal. I mean, however, it's a non-trivial calculation, but done formally in the physicist style. And then okay, then you substitute, and then I mean when your minimization will be. What we want to prove is that the external field, it's enough to take gradients for the external field, and provided they satisfy this equation, which is the hydrodynamic equation, and then now if you substitute, the solution, this is an elliptic equation, because it's a second order in space. If you solve this, so you assign your trajectory, and then you want to know what is the field which produces this trajectory, and this is the solution of this equation. And, and then if you introduce, you use, so this is an equation which can be solved, because it's elliptic, and then you get this expression. So you see that here it appears the hydrodynamic equation once you have taken the typical current on the other side. Now this is exactly what you would get from Wenzel and Friedman theory if that equation that I declared without meaning had a meaning. And then, I mean, you go on and you have to find the minimizing trajectory of this functional, and of course these brackets mean integration of space, so it's a scalar product in this sense. Okay.
So, what was K?
K is this quantity here. So it's, you see, on Sager, did not consider space dependence. There was no space dependence on Sager. Once you have the space dependence, this is on Sager matrix, but you have this extra gradients, and u is the function to which you want to apply this operator. Okay, so then you have an Hamiltonian structure associated to that, and the Hamiltonian equations are nothing but the equations which the variational equations are the Euler equation of the variational principle. Well, clearly here I misquoted the equations. Because I mean, I put the wrong reference so the computer could not read. Actually,
So
this
I
formula,
did miss the point there. You were saying that these equations that you derive are Hamiltonian with this relative.
they are Hamiltonian, yes.
And pi is pi the time derivative of
The
rho?
pi is the conjugate variable
Pi is conjugate to
variable
rho.
to rho.
Yes. I see.
So
So there's a Legendre transform.
there is a Laurent transformation. You see that the conjugate momentum has the role of an external field.
Ah, yes, okay.
So because this is the hydrodynamic equations, and clearly the stationary states, I mean, is the zero solution of the second equation, and then it's an equilibrium point of the Hamiltonian equation.
So if I eliminate the pi, I recover but then I would get a second order equation for rho. That's not one you had before. You had no second order.
No, I mean, the hydrodynamic equation remains first order. And this is well, you write them in Hamiltonian form, so they are first order in time.
Yes, I think all I'm confused about is that up until now we've never seen a second order equation for rho. They've all been first order, like continuity and so on.
Well, in complete problem, then you will see that it becomes second order. I think that
so the solution of this equation describes the optimal trajectory.
yeah,
This is,
the optimizing trajectory must be a solution of this equation. There is
but how you choose the boundary condition for pi, for example? How it's chosen?
oh, I mean, you see, it's this Lagrangian is quadratic in the time derivative.
Yeah.
So you do explicitly the Lagrange transform and you define the conjugate momentum.
No, yeah, but how if you want to solve the next equation, you have to fix the initial conditions. So for rho is like the initial fluctuation, no?
Well, that is the final.
The final. Okay.
Yeah. And the initial condition is the stationary state. You have to produce the yes. Anyway, there is an alternative formula, this formula, fundamental formula, that we have not used. I will tell you who are the people involved in this game. But this may be useful. It resembles a gauge theory. It might be useful in problems where you have a geometric constraint. And the advantage of this formula is that the discontinuity equation is taken into account automatically. So at least I will skip this. Now, essential role plays the time reversal. Now, you define time reversal in the usual way it is done in the theory of stochastic processes, in the theory of Markov chain. And so you have that the probability of the time reversal trajectory in the time reversal measure, it's equal. This theta is just the trivial inversion of the trajectory, and at the level of large deviations, this implies that in the time reversal situation, you have the equality of the rate functions. Now, and here I have to introduce physical principles. I have to assume that the time reversal dynamics exists. Now, in the theory of Markov chains exists. But this, I think, is a reasonable assumption because, for example, heat flows naturally from higher temperature to lower temperature. But acting on the system, you can reverse the flow. So it clearly exists. Now, mathematically, this will be the assumption that it exists some field which is able to let the trajectory going backward. And anyway, in lattice gases, this can be done explicitly. Now, if you write what does it mean, this, so we have time reversal dynamics, and also the assumption that the time reversal dynamics admits hydrodynamics. So there are two very strong physical assumptions, which in lattice gases they are verified in those in which where we have control, like a simple exclusion, zero range, or Kipnis-Mercure, Presutti model, and so on. So there is a class of model for which these assumptions are also justified microscopically. But we cannot do it for a gas should be at best described by Newtonian equations with, you have van der Waals forces and so on. Okay. But this is beyond what mathematics is able to do presently. Okay, and so you have this relationship between a trajectory and its time reversal. Now, okay, so this I have said, I assume that there is a hydrodynamics for the time reversal. Now, this time reversal relationship, you see, what I'm saying is not that the system is time reversal invariant, because this is not true. Because, you see, once you put boundary conditions, so you have different boundary conditions, then you have broken parity. The system is not a demand parity invariant. And there is a general law, apparently of nature, which in quantum field theory can be proved, is the TCP theorem. So here we have nothing charged. So once you break parity, you have to break time reversal invariance. So what I'm assuming, like all the people who work at this, is that there exists a dynamics capable of letting the trajectory going backward. Now, this previous this previous relationship has various consequences. Well, by manipulating these formulas and implying that they must be true for any choice of J and any choice of rho, then you get these two relationships. That the current of the original hydrodynamics plus the current of the time reversal dynamics are related in this way. So their sum must be equal to what I call this gradient of dV over d rho is what I call the thermodynamic force. This is already back in Onsager theory was the case. And this guy is the mobility. And then you have this, this quadratic form is the same must be the same integrated over space, must be the same for the direct and time reversal hydrodynamics. Now, let me define what I call, this is a general fact, that you can split your current in a part which is even under time reversal and in a part which is odd. Now I defined what I call the symmetric part, which is related to the thermodynamic force. And then the other part is defined by the difference, because you know the total expression of the current, you subtract this, and then this is defined by the, and this is what I call the antisymmetric current. Now, if you re-express the previous relationships in terms of this JS and JA, you find that these two parts of the current must be orthogonal in a metric given by the mobility. And then if you insert those two relationships, one in the other, this orthogonality relationship takes this form. And now you recognize immediately that this is the Hamilton-Jacobi equation associated to the variational principle. So this is, and now if you write the equation for the hydrodynamics and the time reversal hydrodynamics, you see that this part remains of the same sign and this one changes sign. So just to illustrate, let me first explain something. Just to give you the simplest example of this phenomenon. Take an electron in a magnetic field. Then you have a term due to the magnetic force, and then you have a dissipation term that you find in books on solid state physics. And you see that these two things are orthogonal to each other. And so you have a JS, which is given by this part here, and this is the dissipative part, and this is the Lorentz force. I think this is interesting for the following reason. Things, you see, here there is nothing connected with electricity, but you have things go exactly when you have a system immersed in a magnetic field. You have a term which changes the sign. So think of so you have a kind of duality principle. Think of the Hall effect. The Hall effect, you put a magnetic field, and then you get a transversal current. Okay? Here you create the current by putting boundary conditions, and everything goes as if an external field were created. But there is nothing particularly magnetic in this. Now you can identify the optimal trajectory using this, and then you discover that the trajectory which optimizes is the one. So the trajectory which optimizes, inversed by the time, must be a solution of the time reversal hydrodynamics. So we identify completely with this, and there is an interesting fact. This is was an analogical experiments done by two people in England, and Luczynski actually was an immigrated Russian. And you see, here they did this experiment by creating an analogical machine using stochastic electronic components to solve this Langevin equation, which was an equation non-gradient, so simulates out of equilibrium situations. And then they discovered that the trajectory which creates the fluctuation.
What is y?
Huh?
What is y?
Is two-dimensional.
Oh, there's
Two
an
dimen-
x1 and an x2, there's two components to the x.
Yes, so this x has two components, x and y. And then they discovered that the relaxation trajectory was different from the trajectory which, and they interpreted the experiment with Wenzel and Friday theory, but they did have the notion of time reversal process. So they concluded that this, one should explain why. Now, with the identification gave you before, now you know, because the optimizing trajectory which creates this, the fluctuation is a solution of the time reversal hydrodynamics. So they must be different in general. It's only when you have time reversal invariance that the two are the same. Relaxation and so when you see a fluctuation, really the system is going backward in time.
Well, in order to compute the adjoint trajectory, you need a stationary measure, no? Yeah.
I mean, they measured.
Yeah. But if you want, I mean, what are these lines that they put there?
What are what?
The lines.
The red and the blue lines. One is one
What is the
direction.
trajectory which creates?
No, I understand, but they have also like lines, not only points. Okay, so they should have some formulas for.
I'm not sure whether they have formulas. I don't remember. I mean, it's long ago. It's more than 20 years ago. But once I went to a meeting of these people, they had no idea that this experiment had become popular for people doing non-equilibrium.
But so why it was in nature? I mean,
One was considered a strange thing, the fact that
okay, that the two trajectories are.
are different. Well, then you can calculate explicitly that this angular deviation function for the invariant measure is is the work done, is the energy dissipated along the optimal trajectory. So in fact is, well, you can give other examples where there is this separation of the two currents. Now this is, well, I think this is 1:30, so
You have 10 more minutes because we started a little late.
another 5 minutes.
Yes, and more. I mean, we started about 10 minutes late.
No, because I am only, I mean, I'm just in the middle of the story now.
Ah, okay. 10 more minutes.
Now, if you want, on Monday, I can give you a supplement of 1 hour, but from 10 to 11.
Ah, okay. All right. Let me ask everybody. Would you prefer to come back at 10 to 11? We'd miss lunch, I think, if we stayed here
When?
for another.
When, David?
On Monday.
Yeah, but you leave on Monday.
Yes, but in the afternoon.
Ah.
So,
Okay.
in the
How
morning,
do you for that?
You'd vote for morning, so 10 to 11. 10.
Or this afternoon?
This afternoon, I'm not sure that we can
Okay.
make it, but
I think it can be
Monday's
done.
little Saturday.
We can get up in the morning.
10 until 11 on Monday, so, yes, we
you
maybe.
see, I'm not even in the middle of the story.
10 till, let's see, Monday.
No, because the most interesting
Oh,
part has to
oh, you know,
come.
there's something very simple we can do about Monday, but maybe it takes a little too late. We were.
But there is already a seminar.
Yes, but it's by me, and I can give it to you from 11 till 12:30. Is that too late, 12:30?
Well, 12:30 maybe is a little bit late.
All right, so
But,
we could do 10 till 11:30, perhaps.
Yes, 10 to 11:30.
All right.
I mean,
then.
if you are interested, I don't know, because
Personally, I am. and
I'm speaking.
You want to finish all the slides? So what is the program?
No, I don't want to finish, even with the supplement, I will not be able to finish all the slides. I will tell you something, because all this was preparation.
All right, so let us then do 10 till 11:30.
Then I will tell you about also the people we have who contributed. One is Thierry Bodino. So,
I'm extremely happy about this because then I don't have to give a lecture on Monday.